Mathematicians are so strange.
Yeah.
I bet you some philosopher out there has an essay on that.
All right.
Oh, I'm sure.
Yeah.
Anthony's here. We can start now.
Yeah, like why that argument's wrong. It's like a 40-page thing.
So, welcome everybody to the inaugural algebraic geometry seminar. So this was actually not my brilliant idea. This was, I think Sam could clarify this better, but you and Pat together came up with this, yeah?
Yeah, I told Pat, you should do this on these notes, and then Pat said, okay, and then you did it. So,
And then he came and asked me about it.
Pat didn't do it, you did it. How did you do it?
So Pat's not here yet. He's not back in town until next week. So those of you who don't know him, you will meet him soon. But he'll be giving, I think, our third talk. So this is his brainchild. So hopefully you enjoy this. So the plan is to learn algebraic geometry properly. So this is meant to be, like, you're meant to take away things from the seminar. So if I ever say anything that's not clear, that you don't understand, you'd like clarification on, just bother me. Please bother me. And I'm hoping all other speakers are equally okay with that. So the thing we're following is Ravi Vikil's notes, and the first thing that's covered in the notes after category theory is sheaves. So we're skipping over category theory as an object in itself because algebraic geometry is about more than that. So I'll be sprinkling in the category theory you need to know as it comes up. But I should first tell you why we look at sheaves. Why are sheaves the first thing we should look at? And for this, I want to mention sort of the difference in paradigm between classical algebraic geometry and modern algebraic geometry. So once upon a time, we looked at these things called varieties. That was the classical perspective. And varieties had two ingredients to them. So the first one was a set. It wasn't any kind of set, it was a special kind of set. We had a set of solutions to polynomial equations and some finite number of unknowns. Some m equations and n unknowns, and these are the things you would look at. And so these would cut out some fancy looking object in n-dimensional space, and you could ask things about, like, where it's smooth, what kind of tangent spaces it has, what its dimension is. Questions like these were things that naturally arose. But in order to assist the study of these things, there was a topology placed on these. At this juncture, I'm not going to go into what that topology is, but we will eventually come to it. So this thing is called the Zariski topology. So this lets us talk about subsets of this thing as being open and closed, and this helped us when algebraic geometers discussed maps between these things. You could talk about properties like closedness being preserved under certain types of maps between these, and this was what algebraic geometers worried about prior to, say, about 1950. So then there was a bit of a paradigm shift. There were some brilliant minds like Grothendieck and Serre, and they came up with basically an entire redevelopment of the subject, sort of a very different way of looking at it. So you replace the object of study with a new object. These things are called schemes. And schemes are the thing we're eventually going to be getting to. It's really schemes where all the action happens in modern algebraic geometry. But they can be seen just as in the right way, as a generalization of varieties. So we're just studying a more general class of objects. And these had some ingredients as well. So they start with the same two ingredients. Formally speaking, we have a set underlying a scheme. But then you throw a topology on the set. So we have a topological space underlying the scheme. But then Professor Grothendieck added an extra ingredient to the concoction. And it's not chemical X. It is sheaves. not schemes, sheaves. That would be a meta definition. So presumably, if you're walking in with a typical background in math, you're probably much more comfortable with sets and perhaps topologies on sets than you are with sheaves. So in order to rectify this problem, in order to look at schemes properly, we should understand this third ingredient really well before we do anything else. So that's why the first chapter that we're going to be looking at from the notes is all about schemes, or sheaves. I'm going to do this a lot. Those words are the same in my mind. So, sheaves. The goal for today is to define what a sheaf is, and we're going to look at a really interesting, or an important, motivating example of sheaves, which is a little simpler than the one Vakil undertakes, but it's continuous functions from open subsets of a topological space into the reals. That's the one I'm going to be looking at as the motivating example. So every time I define something, I'll check it against this motivating example, and we're going to see how these properties unfold and why, if this is going to be a reasonable example of a sheaf, it should satisfy all of these properties. And then after we do that, we're going to look at a construction you have associated with a sheaf, which is called a stock. And we're going to look at the definition of that, what you can do with it, and then we're going to look back at our motivating example again and see what it means in that context. So let's get to defining a sheaf. So a sheaf, unhelpfully, is a pre-sheaf with some extra things attached. So I have to tell you what a pre-sheaf is first. And to that end, I make the following definition. So we're going to define a category, and the pre-sheaf is going to be a functor on that category. So if those words don't make sense to you right now, don't worry. I'm going to flesh that out. So I'm going to invent this notation. Vakil doesn't use it, but I want to give this category a name. So we're going to start with a topological space X. So I'll call this thing open of X, which is going to stand in for open subsets of X. So categories have two things. They have a bunch of objects, which are just things you can work with. And then there's morphisms, which are just arrows between the objects. So we only have to say what those are. So the objects, as the name suggests, are open subsets of X. And the way we're going to get morphisms, or relations between these things, the arrows, is that if we have V as a subset of U, then I just draw an arrow from V to U, and that is the unique arrow from V to U. So in particular, if I string containments together, say W is contained in V contained in U, then the containment of W in U that you get by composing those containments is the same as the composition. So this is the thing we're going to work with. And pre-sheafs are going to take this category and send it to a new category. That's what it means to be a functor on this thing. So given X and open X, so pre-sheaf, say script F, on the space X, it's going to start with the category of open subsets of X and dump it into some category C. So usually we're going to be interested in when C is a certain nice categories. So the ones we're going to be looking at usually category of sets, or say abelian groups, rings, or R modules for some ring R. And all of our rings, unless I emphatically say otherwise, are going to be commutative, because algebraic geometry is much better understood in a commutative context, and it's hard enough with commutative rings without going to the non-commutative sense. So what does this mean? What does this functor business mean? Well, we just take the following. I should also, I guess, add a little word here. Contravariant, as in arrow reversing. So the definition unpacks as follows. So for every open subset, I'm going to associate an object living in C. So for each open U, we have some f of u, an object in C. So if the category of the day is rings, then for every open set, I'm going to put a ring. So for every open set, f of u is a ring.
Can we write that, the definition of a category, very quickly?
Sure, I could do that. I will return. So the first thing you have in a category are objects, as I was saying. Now I guess for all of our purposes we could, I guess you technically call this a class of objects because it might be too large to be a set. But you can just think of it as a set. And that's often denoted this way. So for instance, if we're working in category of rings, you just have a bunch of rings, all the rings. And then you have for each pair of objects, we have morphisms between them, which, if you're thinking of, say, rings, would be ring homomorphisms. Now, I think Vakil likes to call it more for morphisms. And these things have properties. We can compose them, and the compositions behave in nice ways. So for each object A, we have an identity map from A to itself. In morphisms from A to A, which acts like the identity map does. So we have the ability to compose morphisms when all that makes sense. So such that if I compose it on one side by any morphism, I'm going to get F back. And on the other side, I get G back, where these are morphisms from appropriate categories to appropriate categories. So they do that. And then, so composition of morphisms is associative.
And only defined when the codomains and domains line up.
Yeah, exactly. So we can only do it, like if you have one from A to B and then from B to C, then you can put them together and get one from A to C. Have I missed any part of the definition, by the way? That looks...
I mean, I guess the only thing is, in a general category, the morphisms don't have to be a set, but
Yeah,
basically everyone requires them to be a set.
yeah.
I think it's just when you're dealing with categories of functors that
Okay, yeah.
stops happening.
Isn't there logical issues if you let your morphisms also?
Yeah, there are, yeah.
Well, if you relax that restriction, then you can quickly define a functor as a morphism in the category of categories.
So that categories, right, like what's the set, what's the class of objects?
Right.
Yeah. Yeah. So yeah, I think keeping it as
This should be
probably a good idea.
sufficient for our purposes, I think, for the most part. So yeah, you can think of this as just being like set functions between sets, or ring homomorphisms between rings, or group homomorphisms between groups. Every time we say the word homomorphism, it pretty much does the job of morphisms in a category. So it's just a way of formalizing this language.
So in this case, there's only one element in each morphism.
That's correct. At most one.
At most.
If V and U are not comparable sets, then there's no morphism from V to U. But if V is actually contained in U, then we get exactly one.
It's kind of a historical question. Did the word morphism or homomorphism come up first? Because like as a
I
student, you see the word homomorphism first, and then morphism now,
Yeah,
which is simpler.
I think it's homomorphism that came first because people studied groups and rings and so on before they studied categories. And this was just a way of saying, hey, we're doing the same thing all the time, so let's just put it into some unifying language. All right. So let's return to this pre-sheaf definition. So we've got a way of taking every open subset and just making a ring or a set or whatever category we happen to like. And then this thing also plays nicely with the morphisms between the objects. So whenever I have an arrow from V to U, which in this particular case just says that V is contained inside of U, then we get a morphism with the arrow reversed. So if we're working in category of rings, this is a ring homomorphism from one to the other. And for reasons that will shortly become clear, these are called restriction maps and denoted res UV. In our motivating example, these are going to actually be restriction maps of functions. And this restriction map has to play nicely with the composition as well. So what that means in our particular context is if I have a chain of containments, so I've got W, V, U, say. Well, because there's a unique map, going around this way is the same as going by this arrow, because there's only one morphism between any two objects. So we say that this diagram commutes, and if this does, then it's got to commute when I apply the functor. These are the appropriate restriction maps. Which just means if I restrict from U all the way down to W, it's the same as if I had restricted from U to V and then from V to W. Just maybe add the word commutes. So that's the setup for a pre-sheaf. If it does these things, it's a pre-sheaf. So I should give you our motivating example, because the definition itself is not very helpful if you don't have a firm example to fall back on. So we're going to take any topological space X. We're going to get a pre-sheaf, which I'm going to call O, calligraphic O. should say presheaf of rings. That's why I keep talking about rings in my examples. So for every open set, I have to give you a ring. And that ring is going to be, as I said earlier, continuous functions from U into the real numbers. So that's what it is as a set. And we can turn this into a ring by adding and multiplying pointwise. Pointwise plus and times. So we've got a ring for every open set, and I just have to tell you how we define these restriction maps between open sets. So if V is contained in U, we let restriction from U to V be ordinary restriction of functions. So all we do is, if I have a function from U into R, I can just restrict its domain to V, and I've got a new function from V into R. And because of the way open subsets of V relate to open subsets of U, this thing is going to be continuous too. It also satisfies this commutativity requirement, because if I restrict a function from U to V and then down to W, it's the same as if I just did that all in one go and restricted down to W. So is everyone with me so far?
Does it follow from the abstract definition that if U's equal to U, then the associated restriction map is the identity?
Yes.
Because there's a unique arrow from U to U, which must be the identity
Yeah.
in the original.
Oh, I think I do have to impose that, don't I? Because functors are, by assumption, take identity maps to identity maps. Yeah, I think that's a... Yeah, yeah.
That would be it.
It's built into the functor business. So yeah, we want to take the identity inclusion from U to the identity map. Whereas UU is the identity map on F of U. Thank you. That's something I totally missed. I'd never even thought about. So this is the motivating example. And when I add the conditions to make this a sheaf, we're going to see that this satisfies those things. And it's sort of the conditions that give you a sheaf are the reasonable conditions that you would want. It lets you connect behavior on large open sets to behavior on small open sets. It lets you go back and forth between these things. Okay. So pre-sheaf is a sheaf if it satisfies two more conditions.
The other one. A sheaf is a pre-sheaf. A sheaf is a pre-sheaf. What other two conditions?
No, I think it's a pre-sheaf is a sheaf. Because we're taking a pre-sheaf and adding axioms to make it a sheaf.
Okay.
So just to finish your example here, so we get a functor from a topological space into the category of rings.
The functor is from OpenX.
Yeah, from open X. Just this category of open subsets of X.
Yeah, sorry, the category of open subsets of X. So a topological space made into a category in the obvious way. And it maps into the category of rings. And I'm trying to figure out what we send the morphism U subset V to. We send it to the restriction. Oh, so...
Yeah, restriction of functions from U to V.
Induces a natural ring homomorphism from O of U to
Yes.
O of U to O of U. Yeah. Cool.
Cool. So the two conditions we're going to throw onto a sheaf, or to make it a sheaf. I'll go one more board and then I'll go back over here. The first one is called identity. I should also introduce some notation here, which I'll do when I introduce this. So if I have two things, so suppose I've got an open cover of some open set U. Of U where U is open. And I've got two elements, F1 and F2, living in here. As a bit of verbiage, the way we say this are that F1, F2 are sections of F over U. That's a verbal shorthand for this. So if I have two of these, F1, F2, such that if I restrict from U to V, or sorry, U to UI, F1, if they restrict to the same things on all the UI, then they were the same to start with. So because we don't like to write this res all the time, we adopt a shorthand also borrowed from restriction of functions. So you'll often see this written as F1 restricted to UI equals F2 restricted to UI. And it's usually nicer to write and read. So this is something that's satisfied by O. If I've got functions on an open set U into the reals, such that if I restrict them to each open set in a cover, that means that they're the same function on each UI. So if I plug in their value at any point, each point lives in some UI. And if I evaluate them at that UI, or at that point, because they agree on UI, their values at that point are the same. So therefore, they're the same function on all of U. I can do that here. So note, O satisfies this. So the other property we're going to impose is called gluability, which lets us glue together a bunch of these sections on an open cover into a section on the whole thing. So again, if UI is an open cover of U, and I'm given sections over each UI, and they have to relate to each other nicely in the sense that they agree on overlaps. If I restrict them to the intersection of any two of these open sets, they should be the same object. If Fi is such that Fi restricted to UI intersect Uj is Fj restricted to the intersection for all I and j. So if they do this, if they agree on overlaps, then I can lift these things up to something defined all on all of U. such that if I restrict it down to UI, I get my fi back. So it's the natural idea of having glued these things together. So this is another thing we can check is true for our sheaf O. So the idea is, in the setup we have here, so I've got an open cover of U, and I'm given functions from UI into the reals in such a way that if I restrict them to the intersection of any two of these open sets, they're the same function. So we want to stick these things together to get a function defined on all of U. So we'll have to define it on every point. Now there should be a natural way to do this. So what if x lives in UI? What should I define f of x to be?
F5x?
Yeah. That seems to be the natural thing to try. I need to evaluate it at something, so I'll use the function that's defined on the set that contains x. And this condition that they agree on overlaps, that if I restrict to the intersection of the two, says that this is well defined. So if x actually lives in uj as well, then if I restrict to the intersection, which contains x, they're the same function. So if I evaluate them at x, I should get the same answer. So we have no issues here. The only thing you might have to check is that what we get is a continuous function after we've glued them together. So well defined by overlap condition. And continuity is going to be, it's going to arise from the way we define this map. So we just need to show that the preimage of every open subset of U is open. So I want to look at the preimage. Well, because of the way this is defined, you can check that this is a union over these FIs. It breaks up like this. This is a verification I'll leave to you. It's just a matter of noting how we've defined the function. And because each FI is continuous, and these are open, this is open and the preimage has to be open, and then I'm just taking a union of a bunch of open sets. So the end result here is open as well.
So F goes to the reals, right?
Yes.
So we want to, so U is a subset of the real, right? Of the reals.
Oh, you're right.
The images of subsets of subsets of the reals, right? So
Yeah.
The UIs are in the U's that are in X.
Yeah, you're right. I'm just taking the preimage of some open subset of R. Yeah. Oh, you're right. Oh, but then you're just looking at, yeah.
You want to intersect with U.
Well, U is a subset of my topological space. Oh, yeah, intersect this with U, you mean?
No, because it's defining U. F is defining U.
Well, what do you mean by open cover? Like, do you mean the
Open cover of U in my topological space.
Yeah, but this image is already, isn't it? Just
It's like, imagine if W was R, right?
Mm-hmm.
And your FIs are all identities. Then the right-hand side is the union of the UIs,
Mm.
right? And
Yeah, there has to be some intersection with W going on.
well, the intersection with U would do it, right?
Yeah.
No, because F is a function from
Yeah.
U to R. No, Fi is already.
Well, FI is already a
It
function
goes
from U,
UI
yeah.
to R, so the preimage will definitely be in UI.
So what does he mean by open cover? Do you mean the union of the UIs equal to U, or do you mean
equal to
It's a
you,
subset.
equal to you.
Okay. Okay, then there's no problem. Yeah.
Okay. But yeah, my notation initially, yeah, thank you. It suggested that I was thinking of everything in terms of subsets of my topological space, but you want to look at pre-images of open subsets of R, and that's what you're really after. Okay. But yeah, it just comes from this piecewise definition of F that we get this phenomenon happening.
In some place it should be important that UIs are open.
Mhm.
I can't just figure out where it is. Why is it important that UIs are open?
Because the union of open sets, right? That's where, that's a role. But
Yeah,
if there's-
images are only open in UI.
Yeah.
Okay.
I can.
Yeah. Yeah, the pre-images are open in UI, but they're all open in U, so then.
I think that somewhere we lost some abstraction, like without noticing it. So when you write F in F of U, right, you mean F in an object of the codomain of your sheaf, right?
Here,
Yeah, but I'm looking at my specific sheaf O. So the objects in O of U are continuous functions from U into the reals.
Is that how we define sheaf?
But I think the general, like, the
Yeah,
definition of,
this is a particular case of a sheaf, but, I mean.
in our definition of it, we're referring back to the example, I think, right?
Yeah. So what is this in general? It's a sheaf, not a sheaf, not a sheaf of rings, but a sheaf, do we care?
Repeat that.
Okay, so, the definition of a pre-sheaf didn't make references, I mean, it's just a functor to any
Yeah.
category.
Yeah.
And now, so we're defining a pre-sheaf as a sheaf is a particular kind of pre-sheaf.
Yes.
And so the codomain does not have to make any reference to real numbers or
No.
sets or anything. In fact, the objects in my codomain don't have to be sets, so that I can't even invoke this expression F in F of U. So let's go add some.
Yeah, so
If they're not.
so implicit in the
Oh,
definition of
second.
sheaf is that, yeah.
Sorry.
Implicit in the definition of sheaf is that I can talk about elements of F of U.
I think if it's not a category where the objects are sets, then you have to impose other restrictions. So people define sheaves valued in things like topo. And then in this case, an element is an arrow from the terminal object into your object. So you have to define it more abstractly.
Right. That'll be a check.
Okay, so yeah, there is a way to fix it, I guess.
But yeah,
But-
you have to impose restrictions on the category C that, or on the codomain category.
Yeah. But these,
You can also do it by imposing like a condition on a certain equalizer diagram. You can also do it like that.
But that's if you have equalizers in the category.
Yeah.
So we need to, I guess, figure out what we're assuming about the codon. Maybe we can just work with the ring example.
yeah. Well, for everything we're going to be doing, and I think it's because Vakil makes it this way, that always when we're talking about a sheaf, the objects are sets, so I can talk about elements of those sets.
Yeah, that's fine. Yeah, that's true.
Yeah, sorry if that wasn't clear, where the example began and the definition ended. But this does complete the verification that we can glue these things together in O. And that's what we were after. So this is our motivating example. It's the thing that is naturally a sheaf. So the next thing we need to talk about, I'm going to give you an example, a quick one, of a pre-sheaf that isn't a sheaf, just so that you're convinced that the extra conditions I threw at you are actually adding something to the discussion. So this is a simplified version of one of Vakil's. He does it from the complex numbers. I'm going to do it with the real numbers. So we'll let a topological space be the real line. And we define f as follows. So given an open subset of the reals, I'm going to let this be functions from U into R that are bounded. And the way I get restriction maps is ordinary restriction of functions. If I restrict a bounded function, it stays bounded.
Use continuous as well, so, right? Continuous and bounded.
I don't actually need continuous here.
Oh, really?
If you add continuous, then that will just be a sheaf.
No, continuous is also bad too.
Yeah, you could assume on top of it that it's continuous, but I don't need to make that assumption.
Thank you.
So we have this gives us a pre-sheaf. Even if it's not continuous, I can still restrict the function and it stays bounded.
Isn't the word continuous in your definition right there? Or am I?
Oh, that's my sheaf O. I've got a new sheaf now.
Okay, okay.
There's a lot of sheaves and functions flying around. So the reason this is not a sheaf, so I should say it is a pre-sheaf, because you basically can use the same argument we used for O. This works anytime you have functions from open subsets into things and use restriction maps. The argument is totally the same. But the reason it's not a sheaf is it fails this gluability condition. And the reason is when I glue bounded functions on open sets together, I don't necessarily get something that's bounded. So consider, I can cover the real line with these open intervals. Oops. From, say, n minus 1 to n plus 1 when I run over all the integers. So the identity map on un is bounded. So all these functions on un belong to my pre-sheaf. But if I want to glue these together to get a function on the whole real line, then I'm going to have to make it the identity function on the whole real line. Because its values at every point are already determined for us. And the identity function on R is not bounded. So gluing falls apart.
What about the first one?
Oh, the identity axiom. That's fine, because of this whole function concept.
Yeah, but what about a counterexample?
So I was actually thinking about that. It looks like if you try to map, say, the space of polynomials, so it seems like if you replace the topology on X with like the standard topology with like the Zariski topology, say, then you should try to map into a ring of polynomials instead, or else you would fail the identity axiom, or something like that.
Might need some thought, for sure. I don't know one off the top of my head.
So long as they are functions, the identity should follow.
Yeah, as long as they actually are functions.
Actually, so if, oh wait, no, yeah, never mind. I thought I had it.
So yeah, you'll have to venture outside the realm of functions.
I think you need something that's something like modulo p for various p, they agree, but then they're two different numbers upstairs. So when you restrict down, it looks like they look the same.
Yeah, you could like somehow define a weird topology in which like reductions mod p are opens
Well, I
and
think your space could be discrete, right? It's just what you're mapping to. It could be like Z mod or something.
you could cook something up maybe. But again, probably needs more thought. The most of the ones we encounter are going to satisfy the identity axiom anyway. Okay. So I want to introduce stocks. And that seems to be as far as I'll get today. So sheaves, in fact pre-sheaves, have these things called stalks, which allow us to zoom in the sheaf at a point. It's basically the intuition you should have here. We're going to zoom in the action around one point. So that should be a topological space. And F be a pre-sheaf. We can do this with pre-sheaves and sheaves on X. If we have a point in X, define the stalk of F at P so as a set, it's going to look like this. We've got some section and open set paired together, such that P belongs to U, and F is a section over U. So we're only looking at open sets that contain U, or contain P. And we're going to subject it to an equivalence relation, which is going to capture this zooming in phenomenon. So F and U is equivalent to G and V if I can find an open set W inside of the intersection, containing P, of course, such that when I restrict down to W, I get the same thing. So if they become equal when I shrink down to a small enough neighborhood of P, that's what it means for these things to be equivalent. And you can run through the check that this is an equivalence relation. Transitivity is the only one that would be not immediate.
So one thing, I mean, this is kind of related to this, but more related to what we said before. You said open X, the collection of all open subsets of X. This includes the empty set. And the question is, where do we send the empty set? And where do you send, so for each other open set, you have a unique map from the empty set into that set. So where do we send this map?
Yeah, the final object is
Yeah, so
the traditional one for sheaves. For pre-sheaves, they tend not to make this
yeah.
extra assumption.
Yeah, from what I found, yeah, you send it to the final object. But yeah, here you have a, so yeah, okay, so in the case where U is the open set, F can only be like, different category rings, it can only be 0. Yes. Like in this
If the empty set is open, or is the open set in the pair,
yeah.
you'll never have it because P doesn't live there.
Good point.
So yeah, for those of you who don't know what final object was, when I answered his question, a final object is something that there's a unique map into it. So for instance, in the category of rings, my favorite running example, the 0 ring is that. There's a unique ring homomorphism to the 0 ring, which sends everything to 0. That sort of business. Or modules, category of modules, that does the job as well. Singleton sets do this job in the category of sets. There's only one map from a set to a singleton, which is to send everything to the singleton.
There's always a map from an object to that thing.
Yeah, for every object in your category, there's a unique map to that object. Okay. So we've got this definition of stalks laid out, and we can do things with stalks if we can do them with our sheaf or pre-sheaf. So if our sheaf spits us out in the category of abelian groups where we can add, then I can add things in the stalk. Or if it spits us out in a category of rings and I can multiply, then we can multiply things in the stalk. So the way this goes is as follows. So for addition, so if we can add sections together, the way in which you add these is to restrict down to a small enough set on which adding them makes sense. So the intersection of U and V is a subset of both U and V, and on there I can add the restrictions. And another verification, if you like, is you can check that this is well defined. Which certainly needs to be checked, but it follows from our equivalence relation.
we're in a category where there's an addition in each object, right?
Yeah, that's why there's if we can add.
Oh, if we can add, okay, I didn't see that.
If you can multiply, it's the
Yeah.
same thing. You would just multiply these together. This is how you carry the structure over.
Well, that wouldn't really be a property of the category. It's kind of like part of the internal structure of the objects of that category.
Yeah. Yeah, that's true.
Will this make it into a ring or a abelian group?
Yeah, this makes it into, if you had a pre-sheaf of abelian groups, this turns it into an abelian group. If you have a pre-sheaf of rings, it turns it into a ring. R modules, same thing. And you can do all those verifications, but you basically get like all the associativity of addition and multiplication just from the fact that it holds in the objects that F maps to. All right. Well, if you're willing to bear with me for just a few more minutes, I have an example that will probably help anchor this for us. So I want to go back to our sheaf O one more time and see what these look like. Because it's going to be, this notion is going to be important for us when we eventually look at schemes. So what do local rings, or geez, I just gave away the punchline. So what do, what do stalks of O look like? And I just said it. Local rings. So by that I mean rings for which there is exactly one maximal ideal. And so the way we do this, well, let's just pick a point. So let P be in our space. So I'm going to define what the unique maximal ideal should be. We'll check that it's maximal, and then we'll check that it's unique. So you can get a hold of this maximal ideal by thinking of it in terms of a ring homomorphism. So I can say phi, from OP into the reals. So the way I'm going to evaluate this is I'm going to plug it in at P. These things, by the way, are called germs. Not the virus kind of germs, but agricultural germs, germs of seeds, if you will. There's a whole lot of agricultural language floating around in this theory. I don't know why. So we're going to evaluate this at P. And this is well defined under our equivalence relation, because if I replace it with another one, GV, that's equivalent, then if I restrict to a small enough open neighborhood of P, they restrict to the same function, so their value at P is the same. So there's no worries. And you can check this is clearly a ring homomorphism. And so it has a kernel, and it's a surjective map as well. So I'm going to use the first isomorphism theorem to get a hold of things. So it's surjective because of constant functions. I can hit any real number by using the appropriate constant function. So the kernel, well, that's just the set of germs such that f of p is 0. Which I'm going to call MP, because this turns out to be maximal. So if we use first isomorphism theorem, OP mod the kernel is going to be isomorphic to the image, which is R. Now R is a field, so OP mod MP is a field, and that means MP is maximal. And uniqueness, well, we get uniqueness because if you're not in this maximal ideal, we can invert the element. So the way this goes is that if, say, capital M is not equal to M and is maximal, we're going to get a contradiction. So M can't be contained in script M, I guess MP, can't be contained in MP because then they'd be the same ideal by maximality. So I can find an element that's in M but not in MP. So by definition of MP, if I evaluate, I should maybe call this GU. If I evaluate G at P, I'm going to get something that isn't 0. But now by continuity, I can find an open set on which G avoids 0. So there's V open, obviously containing P, with, say, G restricted to V, not the 0 function anywhere. At all points. So then I can define an inverse for GU right away, because then I can take the pointwise inverse of G at every point in V. U intersect V to be safe. 1 over G. Is the identity on U intersect V, which is our identity element. So then M contains a unit, it contains 1, so M has to be the whole ring, and we have a problem. There. All right. So today we learned about sheaves. We looked at the motivating example for sheaves, which are continuous functions from open subsets into R. We defined the stalk of a sheaf, which is what you get when you zoom in really close, and then looked at what we get for stalks of our motivating sheaf. And these things are all local rings. These things are called locally ringed spaces and are going to be very important for us when we eventually look at sheaves. So next week's speaker is Deanna. She'll be taking over next week and telling you more about sheaves, in particular things called the constant sheaf and the push forward of a sheaf, which lets you take a sheaf on one topological space and move it to a sheaf on a different topological space. So I hope this was informative. Please come find me and ask questions if you didn't get anything I said today. And I hope to see you next week.